Tonight, we embark upon a cosmic journey, a slow, gentle drift through the enigmatic beauty of Saturn, that jewel of our solar system, shrouded in mystery and adorned with its unparalleled rings. We will delve into the incredible story of a mission that dared to touch its swirling clouds, to listen to its silent songs, and to unravel some of its deepest, most baffling secrets. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. When our thoughts turn to Saturn, it's almost impossible, truly, to overstate the profound fortune we experienced, the sheer gift of the Cassini-Huygens mission. This remarkable endeavor, a testament to human ingenuity and perseverance, stands as a towering achievement in our quest to understand the cosmos. While a handful of robotic probes, 4 in total, have ventured to gaze upon Saturn from afar, it is Cassini-Huygens that, without a doubt, left the most indelible mark, both in its literal, physical interaction with the Saturnian system and in the sheer scientific volume of its legacy. The data it painstakingly gathered, bite by bite, over years of dedicated observation, has formed the very bedrock, the foundational knowledge upon which more than 4,000 scholarly research papers have been built. Imagine, if you will, the sheer volume of discovery, the countless hours of analysis, all stemming from the diligent work of this single, intrepid explorer. It was this mission that unveiled 6 previously unknown moons, tiny, silent worlds orbiting in the vastness, each now a new point of study, each adding another intricate piece to the grand tapestry of the Saturnian system. Not only did it find these new celestial companions, but it also provided an unprecedented, intimate understanding of their very composition, peeling back the layers of their icy or rocky exteriors to reveal their hidden secrets. The journey itself was an epic, a silent odyssey spanning 2 decades, covering an unimaginable 7 billion kilometers through the cold, dark expanse of interplanetary space. For 13 of those years, Cassini-Huygens gracefully orbited Saturn, a patient sentinel, relentlessly gathering an astonishing array of data. It meticulously mapped the subtle nuances of Saturn's gravitational field, charted the intricate dance of its magnetosphere, gazed upon the majestic, ephemeral beauty of its rings, and probed the swirling depths of its atmospheric structure. And even as its mission drew to its inevitable, dramatic close, Cassini remained steadfast, a dedicated scientist to its very last breath. It continued to transmit precious data, a final, urgent torrent of information, right up until the very moment of its dramatic, fiery plunge. This grand finale saw it descend into the mustard-colored, swirling clouds of Saturn's upper atmosphere, a final embrace with the giant it had studied for so long, ultimately breaking apart into countless pieces, dissolving into the very world it had come to know so intimately. Couple all of this, if you can, with the fact that this mission also gifted humanity some of the most breathtaking, awe-inspiring images ever captured of Saturn and indeed, of the entire solar system. These visuals, often bathed in ethereal light, have forever changed our perception of cosmic beauty, offering glimpses into alien landscapes of unimaginable grandeur. When you consider the sheer scope of its journey, the depth of its scientific contributions, and the stunning visual legacy it left behind, you truly have, in Cassini-Huygens, one of the most remarkable, most impactful missions ever conceived. If one wishes to truly behold the unparalleled beauty of Saturn, to grasp its silent majesty, there is, arguably, no more profound or poignant way to do so than through the yes of Cassini, particularly during its extraordinary grand finale. This final act, a ballad of science and sacrifice, was a culmination of decades of planning and years of relentless observation. Before Cassini, other pioneers paved the way. The first probe to successfully reach Saturn's distant realm was Pioneer 11, a brave robotic scout that arrived in the year 1979. It was during this pioneering flyby that scientists received confirmation of a long-held suspicion Titan, Saturn's largest moon, possessed a substantial atmosphere, a thick, hazy veil unlike any other moon in our solar system. This revelation immediately ignited a fervent desire within the scientific community to return, to explore this intriguing moon more intimately, perhaps even with a dedicated lander. At that specific juncture in time, both Voyager 1 and Voyager 2 were already well underway on their own epic journeys, hurtling through the vastness towards Saturn. Naturally, given their advanced stage of travel, it was simply too late to integrate a lander into those existing missions. And so, from this pressing scientific need, the ambitious concept of Cassini-Huygens was born. It was meticulously designed, painstakingly constructed, and finally, in the crisp autumn month of October 1997, it was launched into the silent, waiting embrace of space. Guiding a spacecraft across the immense chasm separating Earth from Saturn is a monumental undertaking, a feat of celestial mechanics requiring exquisite precision and patience. The entire, arduous trip was a continuous battle against the dominant gravitational pull of our own sun, which tirelessly sought to reclaim Cassini, to drag it back into the warmer, inner reaches of the solar system. To overcome this relentless pull, and to achieve the staggering velocities necessary to reach Saturn's distant orbit, Cassini employed a series of ingenious gravitational assists, leveraging the immense masses of other planets. It executed 2 daring flybys of Venus, swinging close to our scorching neighbor, before gracefully returning to the familiar gravitational embrace of Earth. Our planet's powerful gravity then acted as a cosmic slingshot, flinging Cassini with incredible force towards the king of planets, Jupiter. Jupiter, in turn, delivered the final, decisive gravitational push, imparting the colossal momentum required to propel Cassini across the remaining vast distances and into the waiting arms of Saturn. This specific, fortuitous alignment of planets, which allowed for such perfectly timed and executed gravity assists, is an exceedingly rare cosmic dance, occurring only once every 600 years. This meant that the timing of Cassini's launch and its subsequent trajectory was not merely important, but absolutely crucial, a narrow window in cosmic time that had to be met with flawless execution. And Cassini truly sailed close to the edge. During its second pass by Earth, it skimmed a mere 100 kilometers above our planet's surface at its closest approach, a dizzying, breathtaking proximity that underscored the precision of its orbital ballot. This already fascinating detail becomes even more profoundly interesting when one considers the very source of Cassini's tireless power. It was not, as many might assume for a deep, space probe of that era, powered by vast arrays of solar panels. Instead, its lifeblood, its enduring energy, came from 3 specialized devices known as radioisotope thermoelectric generators, or RTGs. These remarkable units derived their electrical power from the steady, predictable decay of approximately 33 kilograms of radioactive plutonium. It was this controlled, continuous radioactive decay that provided Cassini with its unwavering power supply, generating a consistent flow of electricity throughout its extended mission. Even at the very twilight of its operational life, it was still producing a respectable 700 watts of power, a testament to the longevity of RTG technology. However, the presence of such a significant quantity of radioactive material aboard the spacecraft naturally presented a serious, albeit remote, risk. Had the scientists' intricate calculations been even slightly off, had there been a catastrophic failure that resulted in Cassini crashing back to Earth, the potential for widespread exposure to radiation would have been a grave concern. In the highly improbable, worst-case scenario, estimations suggested it could have led to as many as 5,000 cancer-related deaths. Yet, after rigorous analysis, This risk was ultimately deemed acceptable, with the probability of such an event occurring calculated at an incredibly low 1 in a million. The decision to employ RTGs was a pragmatic one, born of necessity. At the time of Cassini's conception and launch, solar panel technology simply wasn't advanced enough, nor efficient enough, to adequately power a spacecraft operating at the immense distances of Saturn, where sunlight is significantly attenuated. With its RTGs, Cassini was assured of an exceptionally long operational lifespan, a persistent source of energy that might, theoretically, still be sustaining it even now, were it not for the simple, practical limitation that it eventually exhausted its maneuvering propellant. Cassini's mission objectives were numerous and ambitious, a comprehensive blueprint for unraveling the mysteries of the Saturnian system. It sought to achieve a deep, intricate understanding of the structure and dynamic behavior of Saturn's magnificent rings, to explore its diverse family of moons with unprecedented thoroughness, to precisely measure the complex, sprawling magnetosphere of the gas giant, to meticulously study Saturn's swirling atmosphere, and, perhaps most extensively, to investigate the enigmatic moon Titan. This final objective, the extensive study of Titan, is where the Huygens part of the Cassini-Huygens mission gracefully enters the narrative. Huygens was not merely a component of Cassini, it was a dedicated lander, a distinct, autonomous probe specifically designed to delve beneath the thick, hazy, orange clouds of Titan, to see what secrets lay hidden beneath its opaque atmosphere. This remarkable lander represented the European Space Agency's AESA significant contribution to the mission, having been built and operated by their expert teams. The Huygens probe itself was a compact marvel of engineering, measuring approximately 1.3 meters in width and weighing a robust 300 kilograms. After a long, silent journey tucked safely aboard Cassini, Huygens finally detached from its orbiter parent, beginning its solitary, 22-day drift through the cold vacuum of space, on an intercept course with Titan. During this quiescent phase, the only active system aboard the probe was a meticulously programmed wake-up timer, set to rouse the probe a mere 15 minutes before its dramatic entry into Titan's dense atmosphere. And when that moment arrived, when Huygens finally stirred from its long slumber and began its descent, what it encountered was truly astonishing. The descent itself, a 2.5-hour plunge through Titan's alien skies, was the primary focus of Huygens' mission. The probe was equipped with a suite of sophisticated instruments designed to take continuous readings of the atmospheric pressure, its chemical composition, the fierce wind speeds, and myriad other environmental parameters. Because its core mission was so heavily focused on these atmospheric measurements, its onboard battery life was not designed to last significantly beyond the landing itself. The scientific team, at the time, harbored a tantalizing hypothesis that Huygens might land upon an ocean or a vast lake, as liquid features had been hinted at by earlier observations. Consequently, the lander was designed with the capability to float, should it encounter a liquid surface. However, what the images and data ultimately revealed was something different, yet equally captivating. Huygens came to rest on what appeared to be the bed of a dried up lake, a landscape sculpted by ancient, perhaps long vanished, rivers of liquid methane. The broader Cassini mission, in its entirety, proved to be an astonishing success, far exceeding even the most optimistic expectations. Beyond the invaluable scientific data it meticulously collected over those 13 years in orbit, it also captured and transmitted some of the most profoundly stunning images ever obtained of space. The sheer artistry of these cosmic portraits is almost beyond words. The beauty of Saturn itself, with its intricate cloud bands and the mesmerizing dance of its rings, is showcased in these images with unparalleled clarity and emotional resonance. And of course, Saturn's diverse family of moons, each a unique world unto itself, are rendered in their own breathtaking splendor. It's a testament to the mission's rich visual legacy that dedicated individuals have even compiled the staggering 1 million photographs taken by Cassini into breathtaking time lapses, allowing us to experience, however vicariously, what it might have been like to sit aboard the spacecraft, silently drifting through the Saturnian system. These are not computer-generated fantasies, they are real images, meticulously stitched together, color-corrected, and subtly enhanced to convey the subtle, graceful movements of these celestial bodies. There is no CGI here, only the raw, unadulterated wonder of reality, rendered through the lens of a distant robotic eye. It is, quite simply, amazing. As Cassini's precious supply of maneuvering fuel began to dwindle, reaching critically low levels, the scientists faced a crucial decision. They began to meticulously consider how best to extract the absolute maximum amount of data from the remaining operational lifespan of the spacecraft. To achieve this ambitious goal, they made a bold choice. A series of carefully crafted commands were transmitted across the vast cosmic distances, instructing Cassini to perform an unprecedented series of extremely close flybys of Saturn itself, and of some of its inner moons. These maneuvers would bring the probe closer to the planet and its magnificent rings than it had ever ventured before, pushing the boundaries of its design and the limits of scientific exploration. This daring final phase commenced on November 30, 2016. Cassini embarked on a new, high-stakes orbital ballot, repeatedly climbing high above Saturn's North Pole, then plunging dramatically to a point just outside the narrow, ethereal F ring, which marks the outer edge of the main ring system. It completed 20 such daring orbits, each one a testament to its enduring resilience and the engineer's precision. Then, on the 22nd of April 2017, Cassini executed a final, audacious leap, soaring over the rings to begin its ultimate series of daring dives. This was the true beginning of the Cassini Grand Finale, a breathtaking sequence of loops and plunges that would bring the probe ever closer to its magnificent object of study. With each successive dive, it faced increasingly perilous conditions, navigating the uncharted territory between the planet and the inner edge of its rings. The reward, however, was immense. With each close pass, the data it collected became ever purer, ever more revealing. Until, finally, inevitably, Cassini would fly into the very embrace of Saturn itself, its chance for annihilation becoming not merely probable, but absolutely certain. The official website of the space agency articulated the profound rationale behind this final, self-sacrificial mission. It stated that, as Cassini embarked upon its final plunges during the grand finale, it would gather an incredibly rich and valuable trove of information, insights that the mission's original planners, decades ago, could scarcely have imagined. The spacecraft was tasked with creating detailed, intricate maps of Saturn's gravitational and magnetic fields. These maps, it was hoped, would reveal the planet's internal arrangement, offering clues to its hidden structure, and perhaps even helping to solve the long-standing, perplexing mystery of how fast its deep interior truly rotates. Furthermore, the mission would vastly improve our understanding of the sheer quantity of material contained within the rings, bringing us tantalizingly closer to comprehending their enigmatic origins. Cassini's sophisticated particle detectors would, for the first time, directly sample the icy ring particles being inexorably funneled into the atmosphere by Saturn's powerful magnetic field. And its array of cameras would capture truly astonishing, ultra-close images of Saturn's rings and its swirling clouds, providing views never before seen by human or robotic eyes. No other mission, it was emphasized, had ever explored this unique, perilous region so intimately close to the planet. The knowledge gleaned from these final, daring activities, it was asserted, would profoundly enhance our understanding of how giant planets, and indeed entire families of planets, form and evolve throughout the universe. In its final, poignant act, as it spiraled into Saturn's atmosphere at the very end of its 20-year mission, Cassini completed its journey by performing one last, crucial service. It ensured that the biologically intriguing worlds of Enceladus and Titan, with their potential for harboring life, would never be contaminated by any hardy terrestrial microbes that might have stowed away and survived the arduous journey intact. It was a fitting, almost poetic, conclusion to an extraordinary narrative of discovery. This final, deliberate act of self-destruction was inspiring, adventurous, and, in a sense, deeply romantic, a truly fitting end to a thrilling story of scientific exploration. But let us, for a moment, take a closer, more contemplative look at some of these final, extraordinary moments. During the dramatic Cassini grand finale, the operating agency made a conscious, strategic decision. They became willing to trade Cassini's prospects for extended longevity, which were already diminishing due to fuel depletion, for an unparalleled opportunity, a chance to achieve unprecedented levels of closeness to Saturn. This was, in essence, an easy trade to make, a clear choice, as Cassini was already running critically low on propellant. Its ultimate survival as an operational spacecraft was already off the table, its end was assured. Making this decision, therefore, gave Cassini the green light, the final authorization, to approach the ringed planet closer than any probe had ever dared before, darting boldly in between the vast, shimmering expanse of its rings. But what, precisely, did it observe in these perilous, unexplored regions? Did this unique, intimate perspective, this never-before-seen vantage point, reveal anything new, anything that had previously eluded our gaze? Let us now, slowly and deliberately, examine some of the truly awesome sights that Cassini unveiled during its magnificent grand finale. We begin, as the mission often did, with the mesmerizing moons of Saturn. Cassini, in its final, daring passes, observed some of the planet's smaller, more elusive shepherd moons in truly unprecedented detail, revealing features that were previously mere blurs. Consider, for instance, this incredibly close approach to Atlas, a small, irregularly shaped moon, approximately 40 kilometers in width, gracefully orbiting near the ethereal outskirts of the A ring. What immediately strikes the observer about this particular moon is the remarkable, almost unsettling, absence of impact craters on its seemingly smooth, almost polished surface. This unblemished appearance gives it an absolutely bizarre, almost alien, aesthetic. The prevailing theory suggests that fine dust particles, originating from the nearby rings, are continuously collecting over its surface, particularly accumulating around its equatorial region. This constant deposition of material effectively smooths over any nascent craters, gradually erasing the scars of cosmic impacts, and over immense spans of time, has sculpted Atlas into its distinctive, flying saucer-like disk shape. A similar, fascinating phenomenon occurs with Pan, the second innermost moon of Saturn, a smaller body measuring about 30 kilometers across. Pan resides within the Encke Gap, a distinct, narrow lane within the A-ring approximately 350 kilometers wide. As Pan tirelessly orbits, any stray particles from the rings that wander into its orbital path are gently, yet effectively, swept up by its gravitational influence. This continuous, housekeeping action by Pan is what maintains the Encke Gap, keeping it remarkably steady and constant, a clear demarcation within the swirling ring system. Then there is Daphnis, another elusive shepherd moon. Sadly, Cassini was not able to capture Daphnis itself in quite the same level of breathtaking detail as Atlas or Pan. However, its profound effects on the surrounding ring material are strikingly evident, visible for hundreds of kilometers around its tiny, unseen form. Daphnis is an exceedingly small moon, a mere 8 kilometers in diameter, and it carves its path within a very narrow gap in the A ring, aptly named the Keeler Gap. Despite its diminutive size, its gravitational pull, though weak, is just enough to subtly perturb the nearby dust particles in the ring as it brushes by. This delicate gravitational tug creates magnificent, intricate waves, a mesmerizing ripple effect that propagates through the adjacent ring material. Sometimes, this interaction is even forceful enough to visibly rip material directly out of the ring, leaving a faint, ephemeral trail in its wake. These ripples are not confined to a simple side-to-side motion. They also exhibit a distinct vertical component, rising and falling like miniature, cosmic ocean waves. This vertical displacement is dramatically revealed by the elongated shadows they cast upon the ring plane, especially when viewed at low sun angles. One can only begin to imagine the surreal spectacle it would be to sit upon the surface of Daphnis, a silent observer watching these gravitational waves endlessly follow its orbital path, with the glorious, immense presence of Saturn and its countless other moons suspended in the background. It would undoubtedly be quite the sight to behold, a quiet, profound moment in the cosmic ballet. Speaking of the rings themselves, Cassini, during its grand finale, succeeded in capturing some truly spectacular images, revealing their intricate beauty in unprecedented detail. One of the most captivating of these, a personal favorite, showcases what is known as the Janus 291 spiral density wave. What you are witnessing in this image, incredibly, is the result of the very same fundamental process that gives rise to the majestic, sweeping arms of spiral galaxies, albeit on a vastly different scale and in a much more tightly wound configuration. What might, at first glance, appear to be many separate, distinct rings, is in fact an illusion. It is actually comprised of only two magnificent spiral arms, gracefully looping around the planet countless times. This means that every second line you perceive within the image actually belongs to the very same, overarching spiral arm. This particular image captures a segment of the B ring, specifically at a position where the ring particles orbit Saturn, exactly twice for every single orbit of Saturn's moon, Janus. This precise, rhythmic relationship creates what is known as an orbital resonance, a gravitational synchronicity that carves and shapes the ring's structure. The photograph, in its composition, creates a compelling illusion that the entire image is subtly tilted away towards the upper left. However, this is not a true tilt of the ring plane itself. Instead, this visual trick is masterfully created by the way these density waves propagate outwards from the planet. The wavelength of these subtle disturbances progressively decreases with increasing distance from the point of resonance, giving rise to this fascinating perspective. And this is where the resonance, the intricate gravitational dance, becomes even more mind-blowing in its implications. Janus, the very moon that plays a crucial role in shaping this resonance, is not a static entity in its orbit. It periodically switches positions, approximately every 4 Earth years, with its close orbital neighbor, the moon Epimetheus. Each time this celestial swap takes place, the rings respond, a ripple effect echoing through the icy particles, creating a new crest, a new wave, within the existing density wave pattern. The Space Agency, in describing this phenomenon, noted that the precise distance between any given pair of crests within this wave pattern directly corresponds to 4 years' worth of the wave propagating downstream from the point of resonance. This profound insight means that the intricate wave pattern observed here, frozen in time by Cassini's lens, actually encodes many decades' worth of the orbital history of Janus and Epimetheus. According to this remarkable interpretation, the outermost part of the wave, visible at the very upper left of this image, corresponds to the orbital positions of Janus and Epimetheus around the time of the Voyager flybys in the early 1980s, specifically 1980 and 1981. This was the pivotal period during which Janus and Epimetheus were first definitively proven to be two distinct, separate objects, resolving a long-standing astronomical puzzle. This incredible encoding of history within the ring structure, a silent, frozen record of celestial motion, is profoundly reminiscent of how the rings within a tree trunk silently record the passage of years, chronicling its life story. It is, quite simply, amazing. Beyond these magnificent density waves and other breathtakingly beautiful, highly detailed images of the rings, Cassini also made other intriguing sightings: small, distinctive propeller features, scattered across the rings in a number of specific locations. This particular image, for example, offers a unique dual perspective. Showcasing both sides of the rings, the top portion reveals the illuminated, sunlit side, while the bottom displays the unlit, shadowed side. Scientists employ this comparative viewing technique to meticulously analyze and deduce intricate details, even though the scale of the image is relatively coarse, approximately 500 meters per pixel. The tiny moonlet responsible for creating the propeller might not even be directly resolvable at this scale. One might just discern some faint trace of it in the top, illuminated image. However, what is unequivocally visible is that the moonlet is physically connected to the surrounding rings by a subtle, yet distinct, band of material, a delicate umbilical cord of ice and dust. As previously mentioned, this was not an isolated phenomenon. There were other moonlets, tiny, unseen gravitational sculptors, attempting to carve out their own small gaps within the vast ring system. Here, for instance, is another such feature, found right next to the aforementioned Encke Gap. And here is yet another, arguably the largest and most distinct of all three observed. None of these fascinating moonlets are believed to exceed 2 kilometers in diameter, and their density is likely comparable to that of a humble snowball, composed predominantly of water ice. The last intriguing discovery that Cassini was able to image within the intricate tapestry of the rings involves extremely small, yet solid, objects that have formed specifically around the E-ring. These formations are potentially caused by the subtle gravitational perturbations of some of the shepherd moons orbiting in that region. They appear to be solid, demonstrating a remarkable resilience, as they have evidently survived repeated collisions, crashing into the F-ring a number of times. Each impact, though likely gentle on a cosmic scale, kicks out plumes of dust and smaller particles, which sometimes then even fall into the same orbital path as the original objects, creating a faint, ethereal haze around them, a ghostly trail. The objects themselves are not directly visible in these images, primarily due to this obscuring veil of dust that surrounds them. Finally, let us turn our gaze directly to the planet itself. During the period of Cassini's final, daring flybys, Saturn's northern hemisphere was experiencing the full warmth and light of its summer season. This fortunate alignment meant that its truly remarkable, iconic hexagon, a colossal, 6-sided atmospheric formation encircling the North Pole, was in full, unobstructed view. At the very center of this enigmatic hexagon, a permanent polar vortex churns, within which lies the distinct, defined eyewall of a massive, ancient hurricane, a storm of unimaginable scale and power. Interestingly, and quite dramatically, this polar region appears to be undergoing a striking change in color with the progression of its seasons. As you can observe quite clearly in comparison to images from 2012, where the pole appeared notably darker in hue, the current views show a distinct lightening. With the assistance of other wavelengths of light, beyond the visible spectrum, other massive storms become visible, scattered like cosmic pearls across the planet's vast atmospheric expanse, along with subtle, yet distinct, banded patterns reminiscent of Jupiter's iconic stripes, though perhaps not quite as vivid or chaotic in natural light. Furthermore, due to Cassini's unprecedented proximity to the planet during its grand finale. It was able to capture incredibly detailed views of Saturn's atmospheric horizon. On the left side of this image, for example, a delicate haze can be seen lingering in the stratosphere of the upper atmosphere. This ethereal layer gradually thins and disappears towards the right side of the image, showcasing the complex vertical structure of Saturn's atmospheric layers. When Cassini finally made its ultimate, fateful descent into the atmosphere, entering its tenuous outer reaches, it was initially believed that the spacecraft would not survive long enough to even reach this particular haze layer, given the immense forces it would encounter. However, scientists, at that point, were not overly concerned with the probe's ultimate survival as an intact entity. What was of paramount interest to them was the precise chemical composition of this alien atmosphere. Cassini, in its final, heroic act, would plunge directly into those atmospheric depths, valiantly attempting to gather that crucial information, knowing full well it would be consumed by the very process. These would be the last, invaluable readings that Cassini would ever transmit, a final scientific testament before its fiery dissolution. Yet, even 1 week before its final, self-sacrificial entry into the atmosphere, Cassini was still diligently capturing images, its cameras tirelessly documenting the wonders around it. Some of these final images are truly fantastic, offering a profound sense of the mission's scope and the beauty it witnessed. It is important to remember, however, that Cassini was not equipped with the capability for real-time video capture. The videos, or time lapses one might encounter are, in fact, meticulous compilations, the splicing together of countless individual images, carefully sequenced to create glorious visualizations, offering a simulated experience of what it would have been like to fly with Cassini on its ultimate, one-way journey into Saturn. Not all of these final, breathtaking images, it should be noted, are of Saturn itself. The first such time lapse we will consider dates from September 8, 2017, a mere week before the very end of Cassini's extraordinary mission. One of the primary focal points of Cassini's entire operational life, indeed a cornerstone of its scientific endeavors, was the moon Enceladus. This small, icy world is considered one of the prime candidates in our solar system for potentially harboring life, a tantalizing possibility residing within its vast, subsurface ocean. Cassini, in a monumental discovery, unveiled over 100 distinct water plumes, magnificent geysers erupting through the moon's fractured crust, forcefully ejecting material from this hidden ocean directly into the vacuum of space. This ejected water, immediately freezing in the frigid space environment, has now formed the beautiful, diffuse E ring around Saturn. This particular ring is exceedingly tenuous, incredibly faint, and is only truly visible when it is perfectly backlit by the distant sun, appearing as a delicate halo. It is, quite possibly, the bluest naturally occurring object in the entire solar system, a testament to its icy composition and the way it scatters light. Here, we have a truly remarkable view of Enceladus's profound effect on the densest part of the E-ring. One can clearly observe the plumes, like cosmic breath, both disturbing and simultaneously replenishing the ring material, a constant dance of creation and dispersal. Cassini's final, poignant look at Enceladus's majestic plumes was captured in this truly remarkable time lapse, painstakingly assembled from images taken over a 14-hour period. On September 11th, Cassini found itself near the furthest point of its final, elongated orbit, and from this distant vantage point, it captured this truly beautiful mosaic, rendered in natural light. Visible in exquisite detail are the thickest, most prominent of Saturn's rings, the D, C, B, A, and F rings, stretching across the frame. Saturn's relatively short, distinct shadow can be seen gracefully cast over these magnificent structures, a stark reminder of the planet's immense presence. Saturn's northern hemisphere, as we discussed, was immersed in its summer season during this time, which meant that Saturn's most famous, most enigmatic feature, the colossal hexagon storm, was visible in all its glory, perfectly illuminated. One can also just discern, with careful observation, Saturn's subtle, delicate atmospheric bands, revealed in natural light, hunting at the complex dynamics hidden beneath. What is truly fascinating about this particular image, however, is the way the night side of Saturn, shrouded in darkness, is nonetheless dimly illuminated. This ethereal glow is not from the sun, but is due to light reflecting off the brilliant, icy particles of the rings themselves. This means that Saturn's nights, specifically in the hemisphere facing the sun, never truly achieve absolute darkness. They are bathed in the soft, ambient glow of its own magnificent ring system. Below this luminous halo of the rings, however, where the ring light cannot penetrate, Saturn is utterly pitch black, a vast, silent void. As Cassini began its slow, inevitable approach back towards Saturn on September 1/12, it captured even more images of Saturn's dynamic atmosphere, particularly near the planet's terminator line, that ethereal boundary where daylight gives way to the vast, enveloping night. Here, where the sun hangs incredibly low in the sky, huge, towering cloud structures could be seen, casting immense, elongated shadows that stretched for many, many kilometers across the swirling atmospheric layers. It's easy to be deceived by the apparent intimacy of such images, to imagine a small, close-up view. However, what we are actually witnessing in this scene is a sprawling expanse, approximately 500 kilometers across, a scale so vast that Saturn's immense moon, Titan, could effortlessly fit within the shot. As Cassini drew inexorably closer and closer to Saturn, its journey nearing its dramatic conclusion, on September 13th, it made one last, fleeting appearance at Daphnis. For those with a keen eye, attentive observers will notice subtle ripples not only in front of this tiny moon, but also distinctly behind it. This fascinating phenomenon is a direct consequence of the differing orbital speeds of the rings and the moon itself. The inner ring material, closer to Saturn, orbits at a faster velocity than Daphnis, meaning these ripples effectively overtake the moon, constantly exposing fresh ring material to Daphnis's subtle gravitational influence. Conversely, the outer ring material travels at a slower pace than Daphnis, causing the ripples to lag behind the moon. By the time the ring material, from either side, once again reaches Daphnis's position, the preceding ripples have already smoothed out, a continuous cycle of creation and dissolution. On that very same day, September 13th, Cassini took one final, lingering look around the entire Saturnian system. It captured a distant, poignant view of Titan, the intriguing moon that had been a central focus of its mission, a remarkable world veiled in a thick, orange nitrogen atmosphere. It also gazed upon Saturn's majestic rings with the distinct, yet uneven, F ring just visible, a delicate thread at the very bottom of the image. And as the immense form of Saturn grew ever larger in its view, Cassini cast one last, farewell glance at Enceladus, observing it for a span of approximately 40 minutes, before it gracefully disappeared from view, vanishing behind the curved limb of the gas giant. The very final image that Cassini ever transmitted back to Earth was a sweeping view over the precise region where it would ultimately make its dramatic, fiery plunge into the atmosphere. This area was, at that cosmic moment, shrouded in night. Yet Saturn was not entirely dark. It was softly illuminated by the ethereal light reflected off its brilliant, icy rings, creating a haunting, beautiful glow. On the final, fateful day, September 15, 2017, taking photographs was not among the scientists' priorities. As beautiful and scientifically valuable as those images were, they consumed a significant amount of precious bandwidth, a resource that was now in critically short supply. The overriding objective, the fervent desire of the scientists, was to receive every conceivable bit of real-time data from Cassini before the spacecraft was inevitably destroyed. This was an absolutely unique, unprecedented opportunity. Humanity had never before directly probed the atmosphere of Saturn, a realm of immense pressure and exotic chemistry. When Cassini first encountered the incredibly tenuous, outermost layers of Saturn's atmosphere, it was hurtling through space at an astonishing speed of 123,000 kilometers per hour. At this critical juncture, the remnants of Cassini's precious fuel supply were deployed by its small thrusters, firing continuously to meticulously keep the spacecraft's high-gain antenna precisely aimed at Earth. A slender thread of communication across billions of kilometers. At this moment, Cassini was approximately 900 kilometers above Saturn's visible cloud tops. A mere minute later, these same thrusters were firing at their absolute maximum capacity, straining against the increasing atmospheric drag, desperately trying to prevent Cassini from spinning wildly out of control. The spacecraft was now directly sampling Saturn's atmosphere, a scientific coup, but this rapidly densifying atmosphere was also relentlessly heating Cassini, its friction tearing at the probe's delicate exterior. Just 10 seconds after that, the thrusters were finally overcome. They could no longer compensate for the overwhelming forces. Cassini began to tumble, losing its stable orientation, and the vital communication link with Earth was abruptly severed. At this point, Cassini's onboard computers, sophisticated as they were, would have been frantically attempting to diagnose what was going wrong, to understand the sudden, overwhelming chaos. Its gyroscopes and star trackers, designed to maintain orientation, would have registered the uncontrolled spinning, informing the computer of its desperate situation. It would likely have automatically entered a safe mode, diverting power to critical systems in a futile attempt to right itself, to regain control. A minute or so after that, the relentless atmospheric friction and immense heat would have caused the spacecraft to disintegrate entirely, breaking apart into countless fragments, burning up completely within Saturn's vast, swirling atmosphere, dissolving into the very elements it had come to study. Despite this dramatic, fiery end, when the final data started arriving on Earth approximately 1.5 hours later, the time it took for the radio signals to traverse the immense distance, this concluding phase of the mission was universally deemed a resounding success. Cassini had recorded invaluable data from direct analysis of Saturn's atmosphere, revealing its chemical composition, providing insights into its ionosphere, detecting elusive dust particles within the upper layers, and making precise magnetic field measurements. And perhaps, even more tantalizingly, there may be even more discoveries yet to be uncovered from the vast treasure trove of data that Cassini transmitted, waiting for future analysis. And that, truly, is the most amazing thing about the Cassini mission. It just keeps on giving. Even years after its dramatic end, scientific papers are still being published, new discoveries are still being made, as the immense volume of data it collected is meticulously analyzed, re-examined, and interpreted by scientists across the globe. What, then, have we uncovered from Cassini's extraordinary data in the years since its groundbreaking mission concluded? You are about to find out, but be forewarned. Some of the things Cassini has taught us about Saturn have only served to deepen the planet's mystique, making this already strange world even more enigmatic. You might believe you know Saturn intimately. Its iconic, majestic rings are, after all, the largest and most spectacular in our entire solar system. Its hazy, ethereal yellow surface, a canvas of swirling clouds, is both profoundly enigmatic and instantly recognizable, a signature of its cosmic identity. We know it as the second largest planet, a colossal gas giant. We know it possesses the lowest average density of any planet, so light it would float in water if a bathtub large enough could ever exist. And it is, of course, the sixth planet from our Sun, a distant, golden orb in the cosmic dance. And yet, despite all we know, Saturn remains an enigma, a puzzle shrouded in its own thick atmosphere. There is a vast, profound mystery lurking beneath its obscuring atmospheric layers, a mystery painstakingly uncovered, piece by piece, by the tireless Cassini probe. It is a mystery about which the scientific community still does not have a definitive consensus. Saturn, it turns out, behaves in ways that our conventional models, our established theories of planetary physics, claim should be utterly impossible. These baffling anomalies range from its internal temperature, to the curious alignment of its magnetosphere, and even to the very precise length of its days. What truly is going on with Saturn? And what are our best, most creative attempts at explaining these profoundly baffling phenomena? The Cassini probe, a technological marvel, finally arrived at the majestic gas giant on the first day of July 2004. It was not, as we noted, the very first robotic emissary to reach Saturn. 3 other probes had already performed swift flybys, offering tantalizing, fleeting glimpses. However, Cassini was, without question, the most thorough, the most dedicated of these explorers. As we have already discussed, it spent an extraordinary 13 years gracefully circling the planet, diligently collecting an immense trove of data. It utilized its sophisticated array of spectrometers, magnetometers, and other specialized equipment to probe every aspect of the Saturnian system. The wealth of knowledge it bestowed upon us has been an immeasurable benefit, profoundly expanding our cosmic understanding. Yet, paradoxically, sometimes this new knowledge only serves to deepen Saturn's inherent mysteries. Consider, for example, that immense, geometrically perfect hexagon storm swirling majestically at Saturn's north pole. The straight sides of this colossal atmospheric feature are each approximately 13,800 kilometers long, meaning that our entire Earth could comfortably fit within just one of its edges. As best as our instruments are able to tell, this hexagonal storm does not shift its longitude. It remains remarkably fixed at its location, rotating in perfect synchronicity with the planet itself. This is in stark contrast to the rest of Saturn's swirling clouds, which are constantly pushed and pulled along by the planet's ferocious winds, reaching speeds of up to 1,800 kilometers per hour. This storm is undeniably a strange one, an atmospheric anomaly that continues to perplex scientists. While there have been some fascinating laboratory experiments that have successfully created close approximations of hexagonal patterns in rotating fluids on much smaller scales, a full, comprehensive explanation for Saturn's colossal, persistent hexagon still eludes us. But this enigmatic hexagon is not alone in its mysteries. As the mountains of data, painstakingly accumulated by Cassini, began to be analyzed in the years following the mission's dramatic conclusion, even more perplexing questions began to emerge. It all started with a seemingly straightforward, almost innocuous question: precisely how long is a day on Saturn? Despite observing Saturn in our night sky for thousands of years, a definitive, precise answer to this fundamental question had, astonishingly, eluded scientists. After all, it wasn't as simple as merely looking up at the planet and timing the rotation of a solid, rocky surface. Saturn, as a gas giant, has no discernible, solid surface beneath its swirling cloud cover. Any landmarks that might exist on a hypothetical hard surface deep below are completely obscured by its thick, opaque atmospheric layers. Furthermore, these visible clouds themselves move at varying speeds relative to the planet's core, driven by the powerful, internal winds. Even the magnificent rings, while orbiting Saturn, do so at different speeds, and their motion does not directly reflect the planet's interior rotation. One cannot simply look at how fast the rings orbit and assume that rate is identical to the planet's core. After all, most moons in our solar system do not perfectly synchronize their orbits with their planet's rotation, so the rings are no different in this regard. However, scientists, with their characteristic cleverness, possess alternative techniques for determining the rotation rate of a gas giant. One widely accepted method involves studying its magnetic field. It was hoped that this established technique, which had proven successful for other gas giants, might finally provide the definitive answer for Saturn. Planets with magnetic fields generate them through a process known as the dynamo effect. As the planet rotates, vast quantities of liquid, electrically conductive material in its core churn and shift. This colossal motion of charged molecules generates immense electrical currents, which in turn produce powerful magnetic fields. A key characteristic of this dynamo effect is that, due to the planet's rotation, the magnetic pole is almost invariably offset from the planet's true axis of rotation. If the two were perfectly aligned, the magnetic field would, theoretically, not be stable for long. Therefore, the conventional approach is to detect the magnetic fields around a planet, which Cassini was certainly capable of doing, and then observe how the magnetic pole subtly shifts in a circular path around the planet's true rotational axis. Once the magnetic pole has completed one full rotation, you have effectively measured the length of the planet's day. Only Saturn, it seems, does not conform to these established rules. Its magnetic pole is almost perfectly aligned with its axis of rotation, to an astonishing degree of accuracy, less than 0.1 degrees. And despite dynamo theory emphatically claiming that such a perfect alignment should be impossible for a planet generating its own field, Saturn's magnetic field is undeniably robust and vibrant. Its magnetic moment is a staggering 580 times more powerful than Earth's, and its influence extends far and wide, profoundly shaping the entire Saturnian system. Scientists are currently at a loss to fully explain how this magnetic field originates, given its impossible alignment under conventional dynamo theory. Yet, no other alternative method for producing such a powerful and pervasive field has yet been definitively proven. The prevailing thought is that a planetary dynamo is indeed at play within Saturn's deep core, but some other, as yet unknown, effect is occurring within the planet's vast atmosphere, subtly warping the magnetic field lines, causing them to appear perfectly aligned with the axis of rotation from our vantage point. Or, and this is an even more tantalizing possibility, we might be observing a completely new, previously unconceptualized method of magnetic field generation at work within Saturn. So, it was back to the drawing board, figuratively speaking, for solving the elusive length of a Saturnian day. Fortunately, other forms of radiation proved to be more helpful in this cosmic detective story. Saturn is, in essence, an electrically live system. Charged ions are constantly moving and interacting between the various layers of its atmosphere, and even between its rings and its ionosphere. Scientists observed that Saturn emitted distinctive radio waves as a direct result of all these complex magnetic fields and charged particle interactions. These radio waves exhibited a clear, periodic pattern, rising and falling in intensity. In fact, this rhythmic fluctuation seemed to mirror precisely what one might expect to see as a direct consequence of the planet's rotation. Higher levels of radiation would appear approximately every 11 hours or so. As a result, scientists initially concluded, with a reasonable degree of certainty, that this rhythmic pattern corresponded to Saturn's day length. Their initial estimate, based on data gathered during the Voyager flybys, was 10 hours, 39 minutes, and 23 seconds. There was a confident hope that Cassini, with its advanced instrumentation and prolonged observational period, would be able to significantly improve the accuracy of this figure, perhaps even providing a definitive answer. But then, the data started to reveal something truly bizarre, something that made the situation really weird. Over the course of Cassini's 13 years of meticulous study of Saturn, this measured number, the supposed length of a day, began to subtly shift. It drifted by approximately 1% over the course of a year, sometimes rising slightly, sometimes falling. This almost seemed to imply that the planet itself was altering the speed of its rotation, sometimes speeding up and sometimes slowing down. To be absolutely clear, a planet as colossal and massive as Saturn, a gas giant of its immense scale, should simply not be capable of such erratic, variable rotational behavior. Its inertia is far too immense. As such, scientists quickly concluded that this was not, in fact, happening. Instead, some other, unknown effect must, once again, be muddying the waters around Saturn, subtly distorting the measurements. Some dynamic aspect of the atmosphere, perhaps vast, churning electrical currents or complex plasma interactions, was causing these observed shifts in the magnetic fields, making the radiation fluctuate over time, effectively hiding the true rotation of the planet beneath a cloaking shimmer of electromagnetic noise. Another significant consequence of the planet's powerful magnetic field is the stunning auroras that glow and dance majestically at Saturn's poles. However, while on Earth, our familiar auroras are primarily the result of charged particles from the solar wind interacting with our planet's atmosphere. It is now thought that this mechanism alone does not fully account for the auroras observed on Saturn. Cassini, in its detailed observations, detected that at least some of Saturn's auroral displays occurred irrespective of the activity of the solar wind at the time. This crucial finding implies that a significant portion of Saturn's auroras are non-solar originating, meaning their source lies within the planet itself, rather than from external solar influences. Something truly strange, something intrinsically internal, must be occurring deep inside Saturn to power these enigmatic light shows. Saturn also proved to be hotter than our models predicted it ought to be. It radiates out into the cold expanse of space approximately twice as much energy as it receives from the Sun. While a portion of this excess heat can be attributed to the slow, continuous gravitational compression of the planet, a process known as the Kelvin-Helmholtz mechanism, the remainder required some other, additional explanation to account for it. Ultimately, all of these perplexing observations, the perfectly aligned magnetic field, the fluctuating day length, the non-solar auroras, and the excess heat cried out for some unifying, comprehensive explanation. And, fascinatingly, thanks to the wealth of data meticulously gathered by Cassini, we have begun to discover that the key to unraveling all of these mysteries may lie within the very depths of Saturn's gaseous, swirling atmosphere. Saturn is, fundamentally, a gas giant. It is composed almost entirely of the lightest elements hydrogen and helium. However, it is important to understand that not all of this material exists in a purely gaseous state. Due to Saturn's immense mass, the deeper one descends into its atmosphere, the more intensely the heat and pressure build. Eventually, the pressure becomes so extraordinarily great that gaseous hydrogen is theorized to undergo a dramatic phase transition, becoming liquid metallic hydrogen. Some scientists further theorize that this liquid hydrogen, or perhaps even hydrogen compressed to such an extreme density that it behaves like raining diamonds, continuously falls down into the deepest, innermost depths of Saturn. The immense friction generated by this colossal, ongoing precipitation, this diamond rain, could explain a significant portion of Saturn's unusual internal heat. The remaining excess heat, it is thought, originates from the auroras, even though their precise mechanisms are not yet fully understood. The current hypothesis suggests that these auroras are the product of electrically charged particles, originating from Saturn's rings and moons, being drawn into the planet's atmosphere. Whatever their exact source, these auroras may be generating enough heat to significantly warm the upper atmosphere of the planet. Such extreme temperatures, in turn, create other powerful effects. Where warm atmospheric fronts collide with colder ones, immense, powerful winds are formed. It is theorized that these ferocious winds carry electrically charged ions throughout Saturn's upper atmosphere, and it is these electrically charged dynamic winds that are skewing the data from Saturn's radiation, causing its observed variance and the perplexing fluctuations in the apparent day length. Perhaps such colossal motion of electrical currents might also provide an explanation for why Saturn's magnetic fields appear to be so perfectly aligned with its rotational axis, seemingly defying dynamo theory. This unusual alignment could potentially be caused by a highly conductive layer within Saturn's clouds, moving at a different speed relative to the deeper interior layers, thereby creating its own localized magnetic fields that subtly warp the overall planetary field. At least, so goes this intricate, still developing explanation. In the midst of all these intricate theories and ongoing investigations, it should be made abundantly clear that many of these proposed answers still lack final, conclusive proof. Scientists are diligently trolling through the vast ocean of data provided by Cassini, sifting through every byte, hoping for further, more definitive insights. If these insights are not forthcoming from the existing data, then ultimately, it will require another dedicated mission to Saturn, another intrepid robotic explorer, to journey across the vast expanse and find the definitive answers to these puzzling, profound questions. But what about the truly vexing mystery of the length of Saturn's day? Thankfully, this particular enigma does now have a conclusive answer, and, rather beautifully, the crucial clue, it turned out, lay hidden in plain sight within the magnificent rings after all. Instead of focusing solely on the complex electrical and magnetic effects that Saturn exerted upon its rings, scientists realized that the planet would also exert a profound influence upon them through its gravity. This gravitational interaction is, of course, fairly obvious. However, what proved to be far more insightful was the realization that Saturn would not, in fact, exert this gravitational pull uniformly. Saturn is not a perfectly spherical ball. Its rapid rotation causes it to bulge significantly at its equator, making it the most oblate planet in our solar system. Any subtle variance in its shape, any slight deviation from perfect sphericity, would result in corresponding variations in its gravitational field. Saturn's rings, with their immense expanse and intricate structure, presented a perfect canvas upon which to observe these minute gravitational variations. As Saturn pulled at its rings with a subtly rising and falling force at specific locations, it would be possible to detect tiny, yet measurable, ripples propagating through the ring material. Scientists began meticulously searching for these elusive ripples. By precisely measuring the distances between them and analyzing their propagation patterns, it finally became possible to calculate, with remarkable accuracy, the true, fundamental length of Saturn's day, and the previous estimates, based on radio signals, weren't far off. The definitive measurement, arrived at through this ingenious gravitational analysis, was determined to be 10 hours, 33 minutes, and 38 seconds. And this time, scientists are remarkably confident that they have finally got it right. This mystery, at least, has been definitively solved. And yet, despite this triumph, Saturn's other profound mysteries still persist, awaiting future revelations. The next major mission slated to launch towards the Saturnian system is NASA's Dragonfly, with a planned launch in 2027. However, this ambitious mission will focus primarily on exploring Titan, Saturn's largest and most intriguing moon. Titan is, in many respects, the most Earth-like object in our entire solar system. It is the only moon known to possess a thick atmosphere, composed primarily of nitrogen, remarkably similar to Earth's own atmosphere, albeit entirely devoid of oxygen. It also boasts active rain cycles and vast, liquid lakes and rivers upon its surface, though these are composed of liquid methane and ethane rather than water. Given these extraordinary characteristics, it is entirely understandable why scientists are so eager to investigate this unique world more closely. Still, this means that it may be some considerable time before Saturn's deepest, most perplexing planetary mysteries find their definitive answers. Saturn, in its silent, majestic dance, breathes. Its colossal winds, potentially the very lifeblood of its intricate system, thrum and flow across its vast, swirling atmosphere. The delicate, intricate balance of its powerful magnetic fields and its immense gravity gently coaxes and shapes its magnificent rings, keeping them perfectly aligned. A celestial masterpiece of gravitational artistry. Saturn's rings, for all their grandeur and apparent permanence, are thought to be surprisingly young in cosmic terms. While Saturn itself, like the rest of our solar system, is over 4 billion years old, there is compelling evidence, much of it from Cassini, that suggests these spectacular rings may have only formed within the last 100 million years. And, perhaps more poignantly, they are not eternal. They are slowly, inexorably, draining back down into Saturn's vast atmosphere. In another 100 million years, a mere blink of an eye in astronomical timescales, these beautiful, iconic rings may be entirely gone. This prospect, while a natural cosmic process, evokes a strange sense of sadness. Yet, it also makes one feel profoundly fortunate. If humanity had not arrived on the cosmic stage precisely when we did, if our civilizations had emerged just a little later, we might have entirely missed this breathtaking, ephemeral cosmic sight. It may be unscientific, perhaps, to attribute conscious choice to a planet. To suggest it gives us a gift. But one is nonetheless deeply grateful to have been witness to the enigmatic and wondrous world that is Saturn, a world of silent beauty and profound scientific puzzles. And seeing those enigmas, those wonders, all the breathtaking beauty, all the invaluable scientific data, none of it, truly, would have been possible if it had not been for the incredible, tireless Cassini-Huygens mission. This truly was one of the greatest, most impactful space missions of our time. Did you ever pause to consider whether space is truly silent? We often assume it is, especially when thinking about the transmission of audio or compression waves. But what if you were in orbit around Saturn, equipped with sensitive instruments, listening specifically for radio and plasma waves? The Cassini spacecraft, which devoted 15 years of its operational life to orbiting Saturn, carried aboard it a specialized radio and plasma wave science instrument, or RPWS. This remarkable instrument was capable of picking up the very signals you might now be hearing, emitted by Saturn and its diverse family of moons. These natural radio waves, of course, are not directly audible to the human ear. For our benefit, they have been carefully compressed and converted, transforming roughly 30 minutes worth of the original radio wave data into a single minute's worth of audio waves. This conversion was not merely for the sake of creating a strange or eerie audio file. It served a profound scientific purpose. The objective was to meticulously examine the source of these mysterious radio waves. In the particular case of the audio you might be hearing now, the source was identified as Saturn's auroras. You see, our sun is a dynamic star, continuously blasting out bits of its own mass in the form of electrically charged particles. This constant outflow is known as the solar wind. Planets that possess a strong magnetic field, like Saturn, are surrounded by an immense, protective bubble called a magnetosphere. This magnetosphere acts as a shield, redirecting the bulk of this incoming solar wind around the planet and channeling a portion of the charged particles towards its poles. At these polar regions, the charged particles from the Sun impact the planet's atmosphere, or more specifically, its ionosphere. This energetic impact causes particles within the atmosphere to become excited, or in more precise terms, the collision ionizes these atmospheric particles, causing them to emit electromagnetic radiation. We can observe this ionization with our own eyes on Earth, where it manifests as the breathtaking visible light of the aurora borealis and australis. But auroras also emit radio waves, which require specialized instruments, precisely like the one carried aboard Cassini, to detect. These radio waves then bounce around and propagate within the intricate confines of the planet's magnetic field, which is precisely where Cassini was able to pick them up. How do we know this with such certainty? Through yet another fascinating audio file. What you might be listening to here is the distinct sound of the Cassini spacecraft passing directly through the bow shock of Saturn's magnetosphere. As mentioned, Saturn is enveloped by a colossal magnetic field, its magnetosphere, which dramatically deflects the incoming solar wind around it. For the initial segment of this audio, Cassini is situated outside of Saturn's magnetosphere, in the undisturbed realm of interplanetary space. Here, the radio sources are quiet, and there is a profound calm in the audio. Then, Cassini's orbital path carries it directly through the magnetosphere boundary, a region known as the bow shock. This is the precise location where the planet's magnetic field and the relentless solar wind dramatically collide, creating a turbulent boundary. At this moment, there is a sudden, unmistakable increase in the intensity of the radio waves. Once past this dramatic bow shock, Cassini begins to detect a much greater abundance of radio waves, constantly bouncing and reverberating within Saturn's vast magnetosphere, a distinctly different soundscape from the quiet outside. But Cassini heard far more than just the ethereal whispers of auroras. It also made several extremely close approaches to Saturn itself, listening intently to the planet's internal rumblings. Saturn possesses a thick, dynamic atmosphere, a realm of colossal storms that can span the entire planet. One such powerful storm, for instance, produced a sound like this. What you are now listening to are radio waves, powerfully generated by lightning strikes occurring deep within one of Saturn's immense storms. While this might sound faint, almost puny, it is crucial to remember that this is not an actual auditory representation of sound waves, it is a conversion of radio waves. These lightning strikes are so incredibly powerful, so energetically intense, that Cassini was able to detect their radio waves from its distant vantage point in space. To give you some sense of the immense scale, scientists estimate that the lightning discharges within Saturn's storms are roughly 1,000 times more powerful than a typical lightning strike here on Earth. To achieve such intimate proximity to Saturn, Cassini, at certain points in its mission, had to pass through its magnificent rings during daring flybys. During maneuvers like these, Cassini was listening intently. What you might wonder could possibly be the cause of this particular audio. Cassini was traveling at an extraordinarily high velocity around Saturn, reaching speeds as incredible as 121,000 kilometers per hour. As it orbited through the Janus Epimetheus ring, a particularly faint and dusty ring, it would inevitably impact countless tiny particles. These minute collisions, though individually insignificant, would cause the particles to instantly vaporize, transforming into ephemeral clouds of plasma. These tiny, charged explosions, each a miniature burst of energy, could then be precisely picked up by Cassini's sensitive radio and plasma wave science instrument. These impacts were then meticulously converted into the audio you are now hearing. The increased frequency of these distinct impacts served as a direct indicator of the densest parts of the ring. As the impacts gradually subsided, it signaled that Cassini was moving away from the ring again, a sonic map of its passage through the icy debris. Cassini attempted this daring maneuver again later in its mission, this time through one of the precise gaps, located between Saturn and its innermost D ring. You will likely notice that, initially, there wasn't a perceptible increase in particle collisions during this first pass. At first, scientists theorized that this might be because the gaps between the rings were simply incredibly barren, almost entirely devoid of particles. However, a second orbit through the very same gap revealed something entirely different, something unexpected. This time, and on every subsequent orbit, there was a noticeable increase in particle collisions. So, what accounted for the absence of collisions during that initial pass? As it turns out, there were particle collisions, but none of the particles in that specific part of the gap were sufficiently large for the RPWS instrument to detect. Cassini, however, carried another invaluable instrument aboard the Cosmic Dust Analyzer. This instrument was capable of detecting particles as minuscule as 1/1,000,000th of a millimeter in size. And this highly sensitive instrument did detect an increase in particle collisions during that initial fly through, confirming the presence of even the tiniest grains of dust. After passing through the ring during the second fly through, you will also notice these distinctive rising tones. Scientists are still unsure about the precise cause of these particular sounds, but they are reminiscent of similar phenomena Cassini detected earlier in its mission. The other most intriguing source of radio and plasma waves within the broader Saturnian system is, in fact, its enigmatic moon Enceladus. 2 weeks before Cassini made its final, dramatic plunge into Saturn's atmosphere, it captured these unique sounds as it passed by Enceladus. These remarkable observations vividly demonstrate that Enceladus and Saturn share a dynamic plasma circuit between them, much like the intense electromagnetic interaction observed between Jupiter and its volcanically active moon Io, though perhaps to a slightly lesser extent. However, the sheer strength and complexity of this plasma circuit between Enceladus and Saturn greatly surprised the scientific community. Cassini was also equipped with a highly sensitive magnetometer, an instrument designed to detect and measure magnetic fields. This is what its magnetometer detected during the close flyby of Enceladus. It was able to discern a distinct bending of the magnetic field lines, a clear indication of the presence of a thin, localized atmosphere around the moon. The most probable source of this tenuous atmosphere is the powerful jets and cryovolcanism occurring near the south pole of this tiny, icy moon. This geological activity, characterized by plumes of water vapor and ice particles, draws striking parallels once again to Jupiter's moon Io, with its intense volcanic eruptions. The magnetic fields of both planets interact powerfully with the ejected atmosphere of their respective moons, creating a flux tube, or a continuous current of charged plasma particles, a cosmic electrical connection. There is just one more captivating location within the Saturn system that we must explore through the sounds of Cassini, and that is the magnificent, mysterious moon, Titan. Cassini's very first major objective upon successfully reaching the Saturn system was the deployment and launch of the Huygens probe towards Saturn's largest and, arguably, most interesting moon. While Huygens itself was not equipped with its own RPWS instrument, it carried a suite of other specialized instruments. See if you can guess what this recording represents, captured as it descended through Titan's thick, hazy atmosphere towards its enigmatic surface. If you correctly guessed radar echoes, then well done. Huygens utilized its radar system to precisely determine its altitude above Titan's veiled surface, sending out radio waves and timing their reflection. And what about this? This particular audio clip is, arguably, the most impressive and profoundly moving of any that we have discussed so far. Why? Because it doesn't immediately sound particularly dramatic or awe-inspiring. Until you grasp the profound significance of what it truly is, this is actual audio, captured by a microphone on the Huygens probe as it descended through Titan's dense atmosphere. This is the authentic sound of an artificial object leaving the profound silence of space and diving directly into another world. What you are hearing is precisely what you would have heard had you been sitting aboard Huygens, experiencing its solitary, momentous descent. This imbues the clip with an unparalleled sense of awe and perspective, a visceral connection to an alien world, unlike anything else I have ever heard. Somehow, it is truly incredible to contemplate. We often have stunning visual representations of other planets and moons, but I am genuinely unsure if there is anything quite like this direct, auditory experience out there. And there we have it, the evocative sounds of Saturn and a couple of its most fascinating moons. Today, I am truly thrilled, for I get to share with you the astonishing, multifaceted planet that is Saturn. As far as the planets in our solar system go, this one is probably my favorite, apart from our own Earth, of course. And I believe that by the end of this journey, you may well come to agree with me. Because, thanks to the tireless work of the Cassini probe, we possess an astonishing collection of imagery and data, revealing the profound beauty and intricate workings of this magnificent planet. In this exploration, I will not only provide you with insights into some of the most spectacular images Cassini captured, but will also offer a comprehensive overview of almost everything you could possibly want to know about the sixth planet from the Sun. Saturn is, undeniably, immense. It is a gas giant with an average radius approximately 9 times that of Earth, solidifying its position as the second largest planet in our solar system. I specify average radius because its equatorial and polar radii differ by almost 10%. It measures a staggering 60,000 kilometers at its equator, compared to 54,000 kilometers from pole to pole, a clear demonstration of its pronounced oblateness, its flattened shape due to its rapid rotation. With an average density of around 0.7 grams per cubic centimeter, it is only 1/8 the average density of Earth. However, due to its truly colossal volume, Saturn's total mass is equivalent to over 95 Earths. This remarkably low density makes Saturn, by far, the lightest planet per cubic centimeter, a truly unique characteristic. It is, in fact, the only planet in our solar system that is less dense than water, approximately 30% less dense. So, if one could somehow procure a fantastical bath toy of Saturn, one that faithfully replicated the planet's average density, it would, quite astonishingly, float effortlessly in water. This buoyancy is primarily because Saturn is composed of approximately 96% hydrogen, which is, of course, the lightest of all elements. However, simply considering average density does not tell the full, intricate story of what a planet like Saturn is truly like. Saturn is classified as a gas giant because what we visually perceive of the planet is, quite literally, simply gas, a vast, swirling atmospheric envelope. It does not possess a solid, rocky surface beneath its thick cloud layer upon which one could stand. Nevertheless, Saturn is most certainly not gaseous all the way through. It harbors far too much mass for such a simple composition. As one delves deeper and deeper into Saturn's interior, the pressure progressively builds, becoming more and more intense. Eventually, the pressure becomes so extraordinarily great that the hydrogen ceases to behave like a gas and begins to act more like a liquid. So, in a profound sense, beneath Saturn's visible atmosphere lies an immense, liquid hydrogen ocean. Even further below that, it is theorized that there exists a metallic hydrogen layer, where the pressure is so immense that hydrogen transforms into a state where it behaves like a metal capable of conducting electricity. And beneath that, at the very core, could be a dense, metallic, and rocky core, a truly solid heart hidden deep within the gaseous and liquid layers. We do know, with a degree of certainty, that Saturn possesses an incredibly hot interior, with temperatures reaching an astonishing 700 degrees Celsius at its very core. This is a temperature twice as hot as the surface of our own Sun, a testament to the immense pressures and processes occurring deep within the giant planet. If we were to observe Saturn through the invisible wavelengths of infrared light, a spectrum beyond what our human eyes can perceive, we would witness Saturn's own thermal glow, represented in brilliant, otherworldly shades of electric blue, deep sapphire, and vibrant mint green, particularly visible on its night side, where the sun's light does not directly illuminate. This internal light, this radiant energy, is generated deep within Saturn's core and slowly, meticulously, works its way upward through the layers, eventually escaping into the cold, vast expanse of space. In fact, this infrared imaging technique reveals a fascinating and crucial detail. Saturn radiates 2.5 times more energy into space than it actually receives from the distant Sun, confirming its internal heat source. You may not have immediately noticed it, but Saturn's atmosphere, much like Jupiter's, exhibits a distinct banded pattern, a subtle stratification of its swirling clouds. If you increase the contrast when examining images of Saturn, this banded structure becomes far more apparent, revealing its intricate complexity. However, Saturn's atmospheric bands are generally much less chaotic, less turbulent than Jupiter's, and they tend to be significantly wider, particularly near the equator. Have you ever wondered why Saturn appears to be a distinctive yellow hue? It is widely believed that this characteristic coloration is due to the presence of ammonia crystals, suspended high within the planet's upper atmosphere, scattering sunlight in a particular way. But while the visible atmosphere of Saturn may often appear relatively calm and serene to our distant gaze, the planet is, in reality, an extremely active and dynamic world. The winds that rage across Saturn's atmospheric layers are the second fastest among all the planets in our solar system, surpassed only by the blistering speeds found on Neptune. These winds can reach astonishing velocities, a blistering 800 kilometers per hour, creating a truly formidable environment. Visible storms are also known to periodically erupt and appear on Saturn, like the colossal phenomenon observed in 2011, a storm that persisted for just under a year. Historically, there has been a recurring pattern, approximately every 30 Earth years, where the planet produces what is known as a great white spot. This is a unique, yet relatively short-lived, phenomenon believed to occur roughly once every Saturnian year. However, in recent decades, we have, perhaps surprisingly, spotted a few of these immense storms over the last 30 years, suggesting the pattern might be more complex than initially thought. If it does indeed follow a 30-year cycle, we could anticipate another one appearing anytime now. Sadly, even if such an event were to occur, we would only be able to observe it through the powerful lenses of instruments like the Hubble Space Telescope, as the Cassini mission, our primary robotic observer, concluded its operations a few years ago. Beyond these grand, planet-spanning events, Saturn also hosts a plethora of smaller, yet still powerful storms, within which lightning is frequently produced. Cassini, in its diligent observations, even detected the distinctive sound of thunder, or rather, the radio waves generated by these immense lightning discharges converted into an audible format. While the converted audio might sound weak, or even puny to our ears, it is crucial to remember that this is not an actual acoustic sound wave in a dense atmosphere. It is the radio signature of an incredibly energetic event. In reality, the lightning on Saturn is estimated to be approximately 1,000 times more powerful than the lightning we typically experience on Earth, a testament to the sheer scale of atmospheric forces at play. Still considering the planet's powerful storms, let us now shift our focus to Saturn's poles, where we discover that each pole harbors giant, persistent storm systems. In November 2006, the space agency reported that Cassini had observed a truly remarkable hurricane-like storm inexplicably locked to Saturn's south pole. This colossal storm possessed a clearly defined eye wall, a feature that had not previously been seen on any planet other than our own Earth. The ring of clouds forming this eye wall is strikingly similar to the eye wall of a terrestrial hurricane, but on a vastly grander scale. The clear, calm air in the very center of this storm is warm, much like the eye of an Earth-bound hurricane. However, a crucial difference lies in its behavior on Saturn. This storm is rigidly locked to the pole, rotating in perfect synchronicity, whereas hurricanes on Earth typically drift and wander across the oceans. The North Pole, however, presents an even more extraordinary and enigmatic phenomenon, a persistent, perfectly hexagonal-shaped storm. This colossal polygon of clouds rotates in unwavering synchronicity with the planet itself, not merely with the surrounding atmospheric currents. The straight sides of this polar hexagon are, as previously mentioned, each approximately 13,800 kilometers long, meaning that the entire diameter of Earth could be comfortably contained within just one of its segments. Why, one might ask, does this happen? And to such an immense, planet-spanning scale, the simple truth is, we don't yet fully know. However, the leading theory posits that the precise speed differential and the specific viscosity parameters between the various atmospheric bands in this region are likely within a very narrow, critical margin, allowing for the formation and stable persistence of such an unusual geometric polygon. Laboratory tests conducted since this discovery have successfully replicated similar polygonal formations in circular tanks of liquid that are rotated at different speeds at their center and near their outer boundaries, lending significant credence to this leading hypothesis. Intriguingly, towards the very center of this massive hexagon, yet another distinct eye wall can be found, a nested storm within a storm, further adding to its complexity. While not anywhere near as strong or as turbulent as Jupiter's immense magnetosphere, Saturn does indeed possess a substantial magnetic field, potentially generated in the aforementioned metallic hydrogen layer deep within the planet's interior. This magnetosphere is truly vast, extending far beyond the planet itself, and it is powerful enough to effectively deflect the relentless stream of charged particles emanating from the Sun, the solar wind, and much like other planets in our solar system that possess magnetospheres, Saturn exhibits spectacular auroras, shimmering displays of light at its poles. Their precise location and their varying brightness are strongly dependent on the pressure exerted by the solar wind. When the solar wind pressure increases, the auroras become brighter and tend to move closer to the poles. The fundamental process that produces these auroras is similar on both Earth and Saturn. Electrons from the solar wind stream along the magnetic field lines, which are directed into the planet's upper atmosphere. There, these high-energy electrons collide with atoms and molecules, exciting them to higher energy states. When these excited atoms and molecules release this added energy, they do so by radiating light at different colors and wavelengths. On Earth, this light is predominantly from oxygen atoms and nitrogen molecules, creating our familiar green and red auroras. On Saturn, however, the light is primarily from hydrogen, given its atmospheric composition. For me, personally, the magnificent rings are undoubtedly one of the absolute highlights, the crowning glory of the planet Saturn. Saturn boasts a truly prominent and complex ring system, which consists of 10 continuous main rings. While these rings are primarily named after letters of the alphabet, their naming conventions can be a little confusing, so bear with me as we navigate this intricate system. Starting from the closest to the planet and moving outward, we first encounter the D ring, which is exceedingly faint, almost ethereal. Next is the C ring, followed by the B ring, which is the brightest and widest of all the rings, a truly luminous band of icy particles. Beyond that lies the A ring, which is the last of the large, bright rings. Finally, we reach the F ring, a narrow, braided, and dynamic structure. These rings collectively extend from approximately 66,000 kilometers to a staggering 140,000 kilometers above Saturn's center. They are composed predominantly of water ice, with only small, trace amounts of dust and rocky material mixed in. If we were to examine a cross-section of the brightest rings using ultraviolet light, it would reveal fascinating details. There appears to be a greater concentration of ice towards the outer part of the rings compared to the inner part. The red hues in such an image would indicate sparser ringlets, likely composed of dirty particles, perhaps smaller and more contaminated with rocky material than the pristine, icy turquoise ringlets. If we then look at a picture representing radio occultation, a technique where radio signals are passed through the rings, we can deduce the average size of the individual particles that comprise the rings. Color, in such an image, is used to represent information about ring particle sizes, based on the measured effects of three distinct radio signals. Shades of red would indicate regions where particles are, on average, larger than 5 centimeters in diameter. Green would show particles smaller than 5 centimeters, and blues would highlight particles less than 1 centimeter in size. Overall, it is believed that the vast majority of particles in the rings are not larger than 10 meters across, and most are microscopic in size, mere grains of ice and dust. The main rings themselves, for all their immense breadth, are thought to be remarkably thin, ranging from as little as 10 meters thick to, at most, 1 kilometer thick. We can observe that the rings are not perfectly symmetrical. During the planet's equinox, that rare period when the Sun is directly overhead Saturn's equator, the rings can appear somewhat wonky, exhibiting subtle distortions. Look, for instance, at the top of this video, where the B ring meets the A ring. Zooming in on this intricate structure reveals distinct ridges and spokes, some rising a couple of kilometers tall, their presence dramatically revealed by the elongated shadows they cast across the ring plane. Zooming back out, we can then appreciate the sheer scale of how many such spokes appear during this specific period of equinox. These oscillations, these subtle disturbances, happen all the time within the rings, perhaps due to the gravitational presence of a shepherd moon, or even just through natural, internal dynamics. The differences in ring structure, which can be observed over a mere day, can be as substantial as 200 kilometers, highlighting their dynamic nature. So, we've discussed the D, C, B, and A rings, and I also mentioned the F ring. The F ring itself can also become quite wonky, exhibiting fascinating kinks and braids, and it provides a perfect, textbook example of what is known as a shepherd moon. This particular moon is called Prometheus, and it leaves a beautiful, undulating ripple in the F ring as it orbits. Once during its 14.7-hour orbit of Saturn, Prometheus, which is a relatively small moon, only 102 kilometers across, reaches the point in its slightly elliptical path where it is farthest away from Saturn and consequently closest to the F ring. At this precise point, Prometheus's gravity, though subtle, is just strong enough to gently draw a streamer of material, a delicate filament, out of the core region of the F ring, and it is this continuous gravitational interaction that causes the mesmerizing ripples we observe. So, what comes after the F ring in this complex system? Well, this is where the naming conventions can become a little confusing. First, you have the Janus Epimetheus ring, named after the two orbital moons that help define it. Then comes the G ring, followed by the faint Phoebe ring, and finally, the E ring, the outermost of the main, continuous rings. I find this particular picture truly amazing, as these faint, outer rings are much more visibly revealed when backlit by the sun, their icy particles scattering the light directly back towards the camera. This bright, ethereal blue ring you see is the E ring, and you can just barely discern the faint Phoebe ring at the very top of this image. The G ring is the next distinct ring inwards, and again, you can just about make out the Janus Epimetheus ring subtly glowing at the top, just below it. And, incredibly, can you see us? We are all, in a sense, present in this picture too. Here, a tiny, almost imperceptible dot is Earth, accompanied by our moon, a testament to the immense scale of the cosmos. The very last, most recently discovered ring is the vast, diffuse Phoebe ring. This is a truly enormous, yet incredibly sparse, ring that extends far beyond the main ring system of Saturn. It is so gargantuan in its scale that if it were visible from Earth with the naked eye, its apparent diameter would span the width of 2 full moons across our sky. It is believed to have originated from Saturn's 200-kilometer wide moon Phoebe, a heavily battered and scarred body that has clearly endured numerous impacts in its distant past. Phoebe itself orbits just outside of this diffuse ring and likely plays a crucial role in gravitationally containing this dust, preventing it from spreading further outward. On the other hand, it is also suspected that dust particles within this vast ring are slowly, inexorably, falling inward, eventually spiraling down and settling onto the surface of Iapetus, Saturn's outermost regular moon. Iapetus itself possesses a bizarre and striking combination of colors, precisely because dust from the Phoebe ring settles upon its surface. However, because Iapetus is tidally locked to Saturn, always presenting the same face to the planet, only one side of the moon ever consistently faces Saturn, while the backside is perpetually exposed to the incoming dust from the Phoebe ring. This unique orbital configuration means that its 2 distinct faces look profoundly different, one bright and icy, the other dark and dust-laden. So, now that you know a little more about the magnificent rings, I think you'll agree that they are incredibly interesting in their own right, truly fascinating cosmic structures. Theories abound as to why they are there, how they formed, and why they persist, but the simple truth is, we still don't fully understand their origins. We know that some of Saturn's numerous moons are responsible for contributing some of the material to the rings through impacts or gravitational stripping. And, conversely, we also know that some of the material within the rings, through accretion and gravitational clumping, is responsible for the formation of some of the smaller moons themselves, a continuous, dynamic interplay of creation and destruction. And speaking of moons, Saturn has, at the very least, 82 of them. This vast retinue of natural satellites comes in an astonishing array of shapes and sizes. Most uniquely, Saturn's largest moon, Titan, which is even bigger than the planet Mercury, stands alone as the only moon in our entire solar system with a thick, substantial atmosphere around it. This remarkable world, a subject of intense scientific scrutiny, is so captivating that a separate, dedicated exploration is warranted. I'm also going to playfully interject here that Saturn, quite famously, has its very own Death Star, orbiting it, patiently biding its time. We, of course, refer to it by its scientific name, Mimas. Generally speaking, however, most of Saturn's moons are exceedingly small, often only a few kilometers across, little more than captured asteroids or fragments of larger bodies. Lastly, I want to briefly touch upon Saturn's orbit, its grand path around our Sun. Saturn orbits at a considerable distance, approximately 9 to 10 times further away from the Sun than Earth does. Consequently, 1 year on Saturn is a truly vast expanse of time, lasting the equivalent of 30 Earth years. Funnily enough, the length of a day on Saturn is not uniform across the entire planet. It differs depending on where you are situated, whether at the equator or closer to the poles. At the equator or at the poles, a day lasts about 10 hours and 14 minutes. Everywhere else on Saturn, a day is measured at 10 hours and 38 minutes. The underlying issue, the reason for this differential rotation, is precisely because Saturn is not a solid body. It is not bound to rotate at the same precise speed all over its immense gaseous and liquid layers. I simply want to leave you with this profound thought. This final image in your mind: few sights in our vast solar system are more strikingly beautiful, more softly hued, than Saturn, gracefully embraced by the immense, subtle shadow of its own rings. The gas planet's delicate, northward gradation in color, from a rich, deep gold to an ethereal, luminous aurora, is a truly striking visual effect, a cosmic masterpiece that scientists still don't fully comprehend. Current thinking suggests that this mesmerizing coloration may be intimately related to seasonal influences, specifically tied to the exceedingly cold temperatures found in the planet's winter hemisphere. And despite all that we have meticulously learned, all the astounding data we have gleaned from the Cassini mission, Saturn remains, at its very core, a profound world of mystery, an endless source of wonder and scientific inquiry. Thank you for joining me on this journey. This exploration was made possible, in part, by the generous support of all the cosmic explorers on Patreon. If you believe these videos contribute valuable educational content to the world, and wish to provide them with more stability beyond the fleeting whims of algorithms, you can become a paid member on Patreon to contribute directly towards their creation. When you join, you'll be able to watch the entire video ad-free, see your name proudly displayed in the credits, and even submit questions directly to our team for future consideration. Simply sign up using the link in the description. Once again, a huge thank you from myself and the entire team. Meanwhile, please click the link to this playlist for more captivating content. I'll see you next time. The very nature of Saturn's rings, these shimmering celestial ribbons, is one of constant, intricate motion and profound mystery. Beyond the grand, sweeping arcs and broad divisions, Cassini revealed an astonishing array of finer structures, ephemeral phenomena that dance across the ring plane. Among the most captivating of these are the spokes, transient, dark radial features that appear to stretch across the rings, almost like shadows cast by an unseen hand. These spokes are not solid structures, but rather enigmatic disruptions, appearing and fading over periods of hours or days, a fleeting ballad of light and shadow. Their existence hints at a complex interaction between the ring particles and Saturn's powerful, yet puzzling, magnetic field. Scientists theorize that tiny, dust-sized particles within the rings become electrically charged, perhaps by interacting with the plasma from Saturn's magnetosphere, or even from micrometeoroid impacts. Once charged, these minute particles can then be lifted out of the main ring plane, repelling each other and creating these distinct, radial structures that appear darker against the brighter backdrop of the main rings. The exact mechanism, the precise choreography of forces that creates, maintains, and then disperses these spokes remains a subject of ongoing scientific inquiry, a whispered secret that the rings continue to hold. They are a visual reminder of the dynamic, ever-changing nature of this seemingly stable system, a testament to the subtle, powerful forces at play. Beyond the broad, well-defined divisions, the rings are further sculpted by countless narrower gaps and ringlets, each a testament to the intricate gravitational ballet occurring within the system. These divisions are not empty voids, but rather regions of significantly lower particle density, carved out by a variety of gravitational forces. While we've spoken of shepherd moons like Pan and Daphnis diligently maintaining their respective gaps, other, more subtle forces are also at work. Many of these gaps are created by orbital resonances with Saturn's larger, more distant moons. Imagine, if you will, the rhythmic tug of gravity from a moon further out, repeatedly nudging specific ring particles at precisely the same point in their orbit. Over countless cycles, these small, repetitive nudges can effectively clear out a region, much like a cosmic broom sweeping a path, creating a distinct, circular lane within the vast ring plane. The Encke gap, for instance, is not only influenced by Pan, but also by the cumulative effect of countless such resonant interactions, a symphony of gravitational whispers shaping the ring's intricate architecture. Each gap, each narrow ringlet, tells a story of gravitational interplay, a silent record of the forces that have sculpted this magnificent cosmic adornment over untold ages. The F ring, a particularly fascinating and dynamic structure, offers a prime example of this complex gravitational artistry. Unlike the broader, more diffuse main rings, the F ring is notably narrow, often appearing as a delicate, braided strand. This braided appearance is not a solid plate, but rather an optical illusion created by the gravitational interactions of its shepherd moons, primarily Prometheus, and possibly other, smaller, as yet undetected moonlets. These small moons, constantly interacting with the ring particles, subtly pull and push them, causing them to clump together and then disperse, creating transient knots and strands that weave around each other. It's a continuous, dynamic dance where the F ring is perpetually being stretched, compressed, and re-formed by the gravitational whispers of its tiny companions, a living, breathing ribbon of ice and dust. This exquisite complexity, this constant state of flux, underscores the dynamic nature of Saturn's entire ring system, far from the static, unchanging image we might initially conceive. One of the most profound and enduring debates surrounding Saturn's rings centers on their age. Are these magnificent structures, as ancient as Saturn itself, formed alongside the planet over 4 billion years ago, or are they, relatively speaking, much younger, a more recent addition to the Saturnian system? Cassini's data provided crucial new evidence, strongly tilting the scales towards the young ring hypothesis. The sheer purity of the ice particles, their remarkably low contamination by darker, rocky material, suggests they haven't been exposed to the bombardment of micrometeoroids, dust, and space debris for billions of years. If they were truly ancient, they should be much darker, much dirtier, from the accumulated grime of the cosmos. Furthermore, Cassini's observations of the ring's intricate structure, its dynamic, ever-changing nature, and the continuous interaction with its moons, all point towards a system that is still actively evolving, rather than one that has settled into a long-term, stable equilibrium. The current leading theory, bolstered by Cassini's findings, suggests that the rings may have formed from the catastrophic breakup of an icy moon, perhaps a body roughly the size of one of Saturn's mid-sized satellites, or even a captured comet, that ventured too close to the giant planet. This unfortunate celestial body would have been torn apart by Saturn's immense tidal forces, its icy remnants scattering into orbit, gradually forming the magnificent ring system we see today. This event is estimated to have occurred relatively recently in cosmic terms, perhaps only 10 to 100 million years ago. This young ring hypothesis means that we, as humans, are incredibly fortunate to be living in a time when Saturn's rings are at their most spectacular, a temporary, yet breathtaking, cosmic phenomenon that will one day, in the distant future, slowly dissipate and fade away, as the ring particles gradually fall into Saturn's atmosphere. To witness such fleeting cosmic grandeur is a truly humbling experience, a reminder of the vast timescales and dynamic processes that shape our universe. Let us now turn our attention to some of Saturn's other fascinating moons, each a unique world with its own story. Gently illuminated by the distant sun and the glow of Saturn's rings. Beyond the prominent Titan and the distinctive Mimas, there are other icy bodies that hold their own secrets. Iapetus, Saturn's third largest moon, truly stands out with its bizarre, two-toned coloration, a cosmic yin and yang. One hemisphere is strikingly bright, almost pristine white, while the other is dramatically dark, a deep, reddish brown. This stark dichotomy creates an almost cartoonish appearance, making it one of the most visually distinctive objects in the solar system. Cassini's observations help to unravel this mystery, confirming that the dark material is, in fact, dust from the Phoebe ring, the vast, diffuse outermost ring we discussed earlier. As Iapetus orbits Saturn, its leading hemisphere, the side that constantly faces forward in its orbital path, relentlessly plows through this dust, accumulating it over eons. Meanwhile, the trailing hemisphere remains largely untouched, preserving its original icy brightness. Further contributing to this contrast is a process called thermal segregation. The dark, dust-laden areas absorb more sunlight, becoming warmer. This warmth causes the underlying ice to sublimate, turning directly from solid to gas, which then re-deposits as frost on the colder, brighter regions, or on the trailing hemisphere, further enhancing the contrast. This complex interplay of dust accumulation and thermal processes has painted Iapetus with its extraordinary, dual personality, a silent testament to its unique cosmic journey. Then there is Mimas, a relatively small moon, barely 396 kilometers across, yet instantly recognizable for its striking resemblance to the iconic Death Star from science fiction. This uncanny similarity is due to a single, colossal impact crater, named Herschel, which dominates one side of its tiny, icy surface. The crater is truly immense, spanning approximately 130 kilometers in diameter, nearly one-third the size of Mimas itself. The impact that created such a monumental scar must have been unimaginably powerful, a cosmic collision that very nearly shattered the moon into countless pieces. The sheer scale of Herschel crater, with its central peak rising dramatically from the crater floor, speaks volumes about the violent history of the early solar system when impacts were far more frequent and devastating. Mimas, despite its small size, is also a key player in shaping Saturn's rings, specifically by clearing out the 800-kilometer wide Cassini division, the largest gap separating the A and B rings. This is another example of an orbital resonance, where Mimas's gravitational tug, at a specific point in its orbit, repeatedly nudges particles in that region, eventually sweeping them out and maintaining the clear division. Moving to other icy moons, we find Rhea, Saturn's second largest moon, a battered world covered in countless craters, hinting at a long, tumultuous history of cosmic impacts. Yet, despite its ancient, scarred surface, Cassini revealed subtle clues of past tectonic activity, perhaps indicating internal heating in its distant past. There's also Dione, another mid-sized moon, known for its bright, wispy streaks that crisscross its surface. These features, initially thought to be fresh ice deposits, are now believed to be a network of ancient, fractured cliffs, perhaps formed by powerful tectonic forces that once reshaped its icy crust. These cliffs, catching the sunlight, appear brighter against the darker, more ancient terrains. And then we have Tethys, a moon with a truly enormous canyon, Ithaca Chasma, that stretches for approximately 2,000 kilometers across its surface, nearly 3/4 of the moon's circumference. This gargantuan rift is believed to be a consequence of the moon's internal freezing and expansion, causing its icy crust to crack and tear. Each of these icy worlds, silently orbiting Saturn, offers tantalizing glimpses into the diverse geological histories and internal processes that shape celestial bodies, even those far from the warmth of the sun. Let us now return to one of Saturn's most profound and baffling mysteries, one that Cassini's observations only deepened: the enigma of its perfectly aligned magnetic field. As we discussed, conventional dynamo theory, the bedrock of our understanding of how planets generate magnetic fields, posits that a planet's magnetic axis must be tilted relative to its rotational axis. This tilt, this slight misalignment, is considered essential for the continuous churning and fluid motion within the planet's conductive core that sustains the dynamo effect. Without it, the field should, theoretically, rapidly decay. Yet Saturn defies this fundamental expectation. Cassini found that Saturn's magnetic field is aligned to within 0.07 degrees of its rotational axis, an almost perfect, unsettling congruence. This extreme alignment presents a formidable challenge to our current models of planetary interiors and magnetic field generation. The implications of this anomaly are far-reaching. If our understanding of dynamos is correct, then there must be some extraordinary, as yet unidentified process occurring within Saturn's deep interior. One leading hypothesis suggests that a large, stable layer of stratified, perhaps helium rain, acts as a barrier, preventing the deep interior, where the dynamo is likely operating, from mixing with the outer, more fluid layers. This stratification could effectively hide the true tilt of the deep dynamo, making the magnetic field appear perfectly aligned from the outside. Imagine a massive, stable ocean within Saturn, preventing the fluid motion that generates the field from fully expressing its tilt to the exterior. Another possibility, though more speculative, involves the exotic properties of metallic hydrogen under extreme pressures, where its conductivity might behave in ways we don't yet fully grasp, enabling a stable, aligned field. This mystery is not merely an academic curiosity. It touches upon our fundamental understanding of how giant planets form and evolve, how their internal heat is transported, and indeed, how magnetic fields are generated throughout the universe. The precise nature of Saturn's interior, its composition, and its dynamics are inextricably linked to this magnetic anomaly. Future missions, perhaps with instruments capable of probing even deeper into Saturn's gravitational field with unprecedented precision, or with advanced seismic-like measurements, might be able to detect the subtle motions within its core, finally shedding light on this profound puzzle. Until then, Saturn's perfectly aligned magnetic field remains a cosmic enigma, a silent challenge to our scientific models, compelling us to rethink and refine our understanding of these majestic gas giants. The sheer scale of Saturn's interior, the unimaginable pressures and temperatures, is a realm far removed from our terrestrial experience. Below the liquid hydrogen layer, where hydrogen behaves like a metal, capable of conducting electricity, lies the true heart of the planet. This metallic hydrogen is not a solid metal in the conventional sense, but rather a super-pressurized fluid, where the hydrogen atoms have been stripped of their electrons, forming a sea of nuclei and free, floating electrons. This exotic state of matter is believed to be the engine for Saturn's powerful magnetic field, even with its perplexing alignment. Beneath this vast metallic hydrogen envelope, nestled at the very center, is thought to be a dense core, approximately the size of Earth, but significantly more massive, perhaps 10 to 20 times the mass of our planet. This core is likely composed of a mixture of rock-forming elements, such as silicates and iron, along with various ices, water ice, ammonia ice, and methane ice, all compressed to extraordinary densities and heated to immense temperatures. This super-hot, super-dense core is the ultimate gravitational anchor for the entire Saturnian system, the silent, invisible heart of the planet around which everything else swirls and dances. The long-term future of the Saturnian system, while spanning timescales far beyond human comprehension, offers a poignant glimpse into the transient nature of cosmic beauty. As we previously touched upon, the rings, for all their current splendor, are not eternal. The delicate icy particles that comprise them are slowly, relentlessly, spiraling inwards, drawn by Saturn's gravity and buffeted by the subtle drag of its upper atmosphere. This ring rain, as it's sometimes called, means that over geological epochs, the rings are gradually dissipating, their material falling into the planet itself. Estimates suggest that in another 100 to 300 million years, the magnificent ring system we marvel at today may be significantly diminished, perhaps reduced to faint, tenuous bands, or even entirely gone. This understanding imbues our current view of Saturn with a profound sense of urgency and appreciation. We are witnesses to a fleeting moment of cosmic grandeur, a spectacular display that will not last forever. Similarly, the moons of Saturn are not static entities. Over billions of years, tidal forces, the differential gravitational pull exerted by Saturn, have shaped their orbits and internal structures. Moons like Enceladus, with its active cryovolcanism, are constantly evolving, their internal heat sustained by these tidal stresses. However, these interactions also mean that the orbits of some moons are slowly changing, either spiraling outwards or inwards. In the very distant future, some moons might migrate away from Saturn, while others might eventually fall into the planet or be torn apart by its gravitational forces, potentially forming new, albeit temporary, ring systems. The Saturnian system, then, is not a frozen tableau, but a slow, majestic cosmic dance, constantly evolving, constantly reshaping itself over eons. The scientific process that underpins missions like Cassini is itself a remarkable testament to human endeavor. The sheer engineering required to design, build, and launch a spacecraft capable of surviving a 20-year journey across billions of kilometers, enduring the harsh vacuum of space, the extreme temperatures, and the constant bombardment of micrometeoroids is almost beyond comprehension. Each component, each sensor, each line of code represents countless hours of meticulous work, rigorous testing, and ingenious problem-solving by thousands of dedicated individuals. And once the data begins to flow back to Earth, the work is far from over. It requires immense patience, meticulous attention to detail, and profound intellectual curiosity to sift through terabytes of raw information. Scientists spend years, even decades, analyzing the data, identifying patterns, developing theories, and painstakingly testing those theories against new observations. The Cassini mission, in particular, provided such a wealth of information that its legacy will continue to inspire and inform planetary science for generations to come, truly an enduring gift from a silent, distant explorer. The elegance of Saturn's system, the delicate balance of its magnetic fields and gravity, the intricate dance of its rings and moons, all combine to create a cosmic masterpiece. It is a planet that continues to challenge our assumptions, to push the boundaries of our scientific understanding, and to inspire a profound sense of wonder. From the silent, icy plains of its moons to the swirling, enigmatic depths of its atmosphere, Saturn whispers secrets across the void, inviting us to listen, to learn, and to dream. Its golden hues and shimmering rings serve as a timeless reminder of the universe's infinite capacity for beauty and its endless reservoir of mysteries waiting to be unveiled. As our long journey through the marvels of Saturn draws to a close, and the echoes of Cassini's incredible mission gently fade into the cosmic background, we are left with a profound sense of awe and a deeper, more nuanced understanding of this majestic gas giant. The mysteries that Saturn still holds, the questions that continue to puzzle us, only serve to enhance its allure, beckoning future generations of explorers and scientists to continue the quest for knowledge. The legacy of Cassini-Huygens is not merely a collection of data points or stunning images. It is a testament to the enduring human spirit of inquiry, our innate desire to reach out into the vast unknown and unravel its secrets. This mission has fundamentally reshaped our perception of the Saturnian system, transforming it from a distant, fuzzy orb into a vibrant, dynamic, and extraordinarily complex world. We have traveled, in our minds, through its tumultuous atmosphere, gazed upon its iconic rings, and explored the icy, geologically active surfaces of its moons. Each revelation, each new piece of the puzzle, has only served to underscore the immense diversity and profound beauty that exists within our own solar neighborhood. Consider, for a moment, the sheer audacity of such an undertaking to conceive, design, build, and launch a sophisticated machine across billions of kilometers of unforgiving space, to have it operate flawlessly for decades, and to then deliberately guide it into a fiery, self-sacrificial plunge, all in the pursuit of pure knowledge. This is the very essence of scientific exploration, a relentless drive to understand, even at great cost. The data that Cassini gathered in those final, dramatic moments, as it tasted Saturn's upper atmosphere, provided humanity with an unprecedented, invaluable glimpse into the very composition and dynamics of the planet's elusive atmospheric layers, information that would have been impossible to obtain otherwise. It was a final, heroic act of scientific daring, a poignant farewell from a tireless robotic explorer. The insights gained into Saturn's interior, its enigmatic magnetic field, and the fluctuating length of its day, have forced us to confront the limitations of our existing models, pushing the boundaries of planetary science. Saturn, in its quiet defiance of our expectations, compels us to think differently, to imagine new physical processes, and to develop more sophisticated theories. It reminds us that the universe is far more intricate and surprising than we often assume, that even the most well-studied celestial bodies can harbor profound, unexplained phenomena. The ongoing analysis of Cassini's vast data archives will undoubtedly continue to yield new discoveries for many years to come, a silent, intellectual harvest that promises to keep Saturn at the forefront of planetary research. Each new paper, each fresh interpretation, adds another layer to our understanding, slowly peeling back the veil of mystery that still shrouds this magnificent world. And the rings, those ephemeral wonders, continue to captivate and inspire. Their surprising youth, their dynamic interactions with the shepherd moons, and their slow, inevitable dissipation, all speak to a cosmic impermanence that is both beautiful and humbling. We are truly living in a special epoch, a fleeting moment in cosmic time when Saturn's rings are at their most spectacular, a breathtaking display that future civilizations, in the far distant future, may only glimpse through ancient astronomical records. To witness such a grand, yet transient, spectacle is a unique privilege, fostering a deep connection to the vast, ongoing processes of the cosmos. The moons of Saturn, too, have been revealed as diverse and astonishing worlds in their own right. From the thick, nitrogen-shrouded atmosphere and liquid methane lakes of Titan, a potential analog for early Earth, to the cryovolcanic plumes of Enceladus, hinting at subsurface oceans and the tantalizing possibility of life, these satellites offer miniature solar systems of their own, each a distinct laboratory for studying planetary formation and astrobiology. Cassini's close encounters with these moons have provided invaluable data, allowing us to reconstruct their geological histories, understand their internal structures, and speculate about their potential to harbor life beyond Earth. The sheer variety among them, from the battered, ancient surfaces of Rhea and Dione to the uniquely scarred Mimas, underscores the intricate and often violent processes that shape celestial bodies. As we conclude this exploration, let us carry with us the spirit of Cassini, a spirit of relentless curiosity, meticulous observation, and unwavering dedication to the pursuit of knowledge. Saturn, with its golden glow and its shimmering rings, stands as a timeless beacon in our night sky, a permanent invitation to look up, to wonder, and to continue our journey of discovery. The universe is filled with such wonders, each one a story waiting to be told, a mystery waiting to be unraveled. And as we drift into the quiet contemplation of these cosmic truths, we are reminded of our place within this vast, magnificent cosmos, forever curious, forever seeking to understand the silent whispers of the stars. The journey of understanding is never truly over. It merely pauses, awaiting the next intrepid probe, the next brilliant mind, to push the boundaries of our knowledge a little further, to illuminate another corner of the universe. The echoes of Cassini will resonate for centuries, a testament to what humanity can achieve when it dares to dream beyond the confines of our home world.